Hello everyone, welcome to this GAIA meetup with Zenuity. My name is Amanda and I'm from the GAIA team, and I'm here sending live from Zenuity today with my colleagues Anna and Adam, who are with me here, and also Erik, who is with us from his home office. Before we start, I would like to say a few words from the GAIA committee. And the first is that we were supposed to have this GAIA conference at 28th of April, but it has been moved now to 22nd of October. So we hope that the current situation will be better by then, and that you all will be able to join the conference in October instead. So while waiting for the conference, we thought it would be nice to have a couple of digital events to fill up the space in between events. So if you are interested in hosting an event at your company, please get in contact with us at GAIA. And this is our first live event, so I hope that everything will work smoothly. And if it doesn't, please bear with us. The live event will be posted on our YouTube channel, the GAIA. And we will have a Q&A session that you can write your questions in during the whole event. And unfortunately, as we wanted to have as many as possible to join this event, there's a slight time delay, like 10 or 20 seconds. So if you don't get an answer to your question directly, please wait a couple of seconds. And now I leave over to my colleague Anna, who will give a brief introduction of Zenuity and of the presenters today. Thank you for joining.
Hi, everybody. My name is Anna, and I'm part of our people team here at Zenuity. I'm super happy to see so many people attending. I see all the time that more and more attendees are joining as well, so I'm really excited about that. I'm even happy that MS Teams didn't decide to go down in whole Europe today, as it did last week, so appreciate that. But to just give you a brief overview of who we are at Zenuity, we want to change people's life and the future of mobility by making self-driving cars real for the first time. And since this is something that since this is a product that nobody has ever succeeded to do on the market yet, our type of work requires cutting-edge technology, lots of innovation, and lots of creativity. So, for example, some of our teams work with deep learning and with traditional computer vision. And in this meetup, we want to share with you knowledge about deep learning and also to engage discussions within this area. So today I have with me my colleagues Adam and Erik, and they're going to talk about deep learning for self-driving cars. So first we're going to start with Erik, and he will be talking about active learning, while after that Adam is going to take over and talk about 3D object detection. Me and Amanda, on the other hand, are going to facilitate this meetup. So as Amanda already said about the Q&A session, we have this opportunity, and it's a lot of people attending this meetup. So please just feel free to write your question. Then me and Amanda are going to see it and forward it to Erik and Adam. You can ask your question during the presentations, for example, or if the question pops after the presentations are finished, you can do it then. So it's your decision. Thank you from me, and now I'm leaving over to Erik Werner, who's going to start with the first topic, and namely active learning.
All right, I'll try to share my screen, and I hope you can hear me. Now I'm showing you my Slack window. That wasn't on intent. So, as Anna said, we're trying to build self-driving cars. Here are the software for self-driving cars. This problem can be divided into three parts. First, you have to perceive your surroundings, and then you have to make a plan for what you want to do, and then you have to act on that plan. So today we'll stick to the perception part, which is arguably the hardest part of the problem. And if you can solve the perception part of getting an understanding of your surroundings, then it's impossible to make a good plan. More specifically, both Adam and I are from the vision area of Zenuity, so we'll talk about making forming an impression of your surroundings with camera images. And even more specifically, we both work with deep neural networks, which, as you know, is the go-to tool for many computer vision tasks nowadays. So my name is Erik Werner, as Anna mentioned. I've been at Zenuity since the start 3 years ago, doing different neural network things. And currently I am in the data and learning team, who are responsible for getting high quality data to train neural networks on, and also validate, of course, and also bringing good data to the other computer vision algorithms that we have at the company. So this slide shows our responsibility. It's the parts of this pipeline that are in green are the responsibility of this data and learning team. So we have collection vehicles out on the road collecting data, and that's then stored on our servers. It's the raw data here. I hope you can see my pointer. Then we do quality checks to make sure that the data is of good order, that the calibrations are okay, and that the sensor quality is good. Then we do the so-called curation step, which is what the focus of this talk will be. So curation means selecting what you want to annotate. So as you know, there's a lot of talk about artificial intelligence nowadays in respect to neural networks, but whether you can call it intelligence is a bit doubtful. So what these neural networks can do really well is to mimic. So in order to be able to solve the task of, for example, locating all the cars in an image, in order to train a neural network to do this task well, at this point in time, you need to have a big database of images where a human annotator has sat down and drawn small boxes on the images. So we need to somehow select what images that we should annotate on. And we cannot send everything to annotation, because if you have a car out on the road that in a week can easily get you millions of images back, and it's too expensive to manually annotate all of them, so you have to select some subset for annotation. And this talk is about a method for selecting that subset in a clever way. So after we have selected images to send for annotation, external annotation companies do the actual annotation for us, and then we get to annotate the data back. We do further quality checks, because we can do more intense quality checks at this point, because it's not as much data as in the first stage, and now we really need to make sure that we have a high quality so that we can train the neural networks on them. So the neural network teams, the function teams, they train the neural networks, and then equally important is to validate them, to make sure that they do what they're supposed to do and don't miss anything important or predict things that aren't there. And also equally important is the deploy part. You have to make sure that these neural networks can run in real time, and that there are no bugs that could lead to dangerous behavior. So it's a very important task for us. Right, but this talk will be about active learning. So active learning represent this arrow here. You close the loop by letting the curation phase be informed by what the neural networks can do. So again, when you select what you want to annotate, instead of doing this randomly or by some heuristic procedure, instead try to let it be informed by what the neural networks can do at the moment, and try to select the images that the neural networks could learn the most from. So I'll start with a toy example to demonstrate how this can be done.
Sorry for interrupting, but we got a question.
Yeah, please.
So I want to share it with you. The comment is, I keep hearing traditional computer vision mentioned. What problems, subtasks are not suitable for deep learning? I guess data augmentation is one example. It seems to be that in general, raw data should be preferable as input for learning methods. So what is traditional computer vision used for nowadays?
Yeah, so one example would be, for example, visual odometry, where so there are many techniques in visual odometry that combine deep learning methods with traditional computer vision methods, but it's not all deep learning, for example. regarding data augmentation, yes, I mean, to design good data augmentation methods, there are papers that try to learn how to do that, but most of the time it's done by a lot of expert knowledge about the domain. So that's a good example also of what currently is usually not solved by neural networks. Anyway, I'll continue with the toy example, unless there were further questions. So this so-called 2 moons example that I have here, it's a classification tasks with the inputs in 2 dimensions. So instead of with an image, you have millions of dimensions, basically 3 numbers for each pixel. Here you have input dimension of just 2, and the task is to classify all these points into one of 2 classes. Now it's of course obvious here what the 2 classes are, but let's pretend that we do not know anything about the structure of this or about what points belong to which class. And let's further imagine that it's expensive to get to annotate. So to get labeled data, you need to pay a large cost. So you want to label as few of these points as possible before you train your network with traditional deep learning or neural network techniques. So I'm going to try to show a little example of how this can be done. Let's see, this is how it works. All right, so now let's imagine that we ask to label 1 point randomly. We get the label back. It turns out that this point here has the label red, belongs to red class, and then we train a neural network on this minute training set that only has a single point in it. Yeah, in this case, if you train your network on a single point that belongs to the red class, it will predict that the whole data set, that all points belong to the red class. So you probably want to label more points to get the sensible predictions. So let's get 1 more point to label, selected randomly. Now by accident, this one was also red, so you haven't really learned anything at all. You get another one. This one was also red. 1 more red point, and so on. So in fact, in this case, by accident, you had to wait until the 9th point before you even get the first example of a blue point. And if we keep on adding label points, what you see is that the decision boundary improves, but probably doesn't improve as fast as it could. So if you see here, hey, we have 19 labeled points, but still there's a large part of the training set that's not correctly labeled. And if you ask for more labels, then most of the time you get a label that doesn't really change the decision boundary much. So if you ask for a label for a point that is already correctly labeled by the neural network as it is, then you haven't really improved your decision boundary, you haven't learned anything. There's not so much information gained from this point. But if you keep labeling points, you see that after a while it improves. So, but even if you have labeled 40 points, you still cannot perfectly find the decision boundary to separate these 2 data manifolds. And in fact, even after 50 label points, there's still a part of the data set that you cannot classify correctly. So this idea of just selecting what points to label randomly, it's probably not the most efficient way to do it if you want to minimize the annotation cost. Let's see. So what can one do instead? Well, if you try to think about the test, what you want to do is to get as much information as possible from each labeling event. And if you know information theory, then you know that you can define information content of an event as the negative logarithm of the probability that this event occurs. So is there some way that one could use this to decide what you want to choose for annotate? Well, one thing, if you train a neural network to solve a classification task like this, what it does is that you feed in an input data point, and then the output you get is a probability distribution over the possible output classes, or at least it's some number that can be interpreted as a probability distribution. So if you take this number that you get out seriously and treat it as a probability distribution, then we can get some sort of information gain by looking at the negative logarithm of the probability that the neural network assigns to this label. And in fact, this negative log likelihood, it's identical to the cross entropy loss that you often train a classification network with. So the cross entropy between the output distribution of the neural network and the target distribution, which is 1 for the correct class and 0 for the other one. So another way to put this is, if you want to select the most informative point, you should select the point which has the highest loss and get the label for that one. So if we do that, let's see, now I lost my mouse, but it should be okay. If we do it, we see that the first point you select is also selected randomly, basically. And then the second point will, by necessity, be a wrongly classified point, because if you make the wrong classification in the first step, then will have a very high loss for all the wrongly classified points that should be red. So you will get a red point in the next step. And similarly, in the next time you ask for a label, you will get something that was wrongly classified. So in this way, by always getting a point that had a wrong label, you relatively quickly improve your decision boundary. So in fact, already after 11 label points, has already found the perfect decision boundary for this problem. If you keep going, it actually breaks again, because the neural network training that I have here isn't very stable. But the good thing about this thing is that whenever you make a mistake like here, this part is classified wrongly, then you will automatically, next time you ask for a label, you will get the label from that part of the distribution. So you automatically correct the mistakes you made in the previous iteration. So after 20 label points or so, you never make any mistakes anymore, basically. There was one, but most of the time it works. And if you had a more stable training algorithm, it would work always. All right. So in this case, we've chosen always the most informative point, but we were cheating, right? Because in order to find the most informative point, we need to know the label before we make the selection, which we cannot do in the real world, of course. But what can we do instead? Well, one thing we can do is to use if we take this probabilistic model that the neural network outputs seriously, then we can use that not to get the information gain, because that depends on a label that we don't know, but we can get the expected information gain, which is also called the Shannon entropy. And the Shannon entropy, that's simply the expected value of the information gain with some overloading of the notation here. I'm sorry about that. You simply sum over all the possible output classes, and you get the probability that the label belongs to a certain class according to the neural network's model, times the information gain in case it does belong to that model. So if we use this expected information gain that we can get instead of the true information gain that we cannot get, then we see how that works. So again, the first point is selected randomly, and then the next point is selected very far from the first point, because that's where you're most uncertain. And then what will happen next is that this expected information gain is always highest when you have this as much uncertainty as possible. So in this case, by picking the most entropic point, the point with the highest expected information gain, that would always be a point along the decision boundary, because that is where the probability of each class is 1/2, and that's where you get the highest expected information gain. So what this thing will do is always pick a point along this boundary. And what you see when you do that is that you relatively quickly, not as quickly as in the previous case, but relatively quickly you improve your decision boundary. And one way to make sense of this is that while you don't always get the most informative point where you did something completely wrong, at least you know that you will learn something in every iteration. Because in every iteration, before you got the label, you thought that it was 50% chance red, 50% black. So either way, whatever it is, you will learn something. And then we see that. Yeah, just give me a few seconds and I'll finish this part. So in this case, after about 20 label points or so, we have found the perfect decision boundary. All right, please go ahead.
Yeah, so the question was, how do you know which points are classified wrongly?
Yeah, exactly. So this post maybe was posted before, because I did this trick of pretending that you could use the label at selection time. So I hope that you're satisfied with this second part of the toy model, where you use the expected information gain instead.
Okay, and then there was another question, if you can take that now. So the question was, in this toy example setup, are we training the model with supervised training paradigm with the same hyperparameters, epochs, batch size, etc., when new data is added in the training data?
Yeah, thank you for this question. I realized I was too fast and forgot to say this. So yes, so what happens is that what you do is as you say, the network is trained purely supervised. So while you see all these black points here, they are not used in training in any way. You only use, in this case, these 2 label points to train a neural network, and that gives you this decision boundary. And then you get 1 more point labeled, and that allows you to train a new neural network, which gives you this decision boundary. And then you add 1 more point, and then you train the neural network again, and you get a new decision boundary, always with the same hyperparameters. And in this case, a very small neural networks, I think, with 2 or 3 hidden layers, and it's around 10 neurons in each or something like that. So a very small neural network that's enough to solve this task. So in this case, the retraining of the neural network is a very fast procedure, so you can add 1 point at a time, and you can basically instantly retrain your network and get a new point and so on. But if we go over to the real world, then you don't have really this leisure. So that's the next part, to go to a more realistic problem. So I've chosen the road classification problem as an example of a more realistic task. So for this, what I talk about today, I'll tell you a little bit about an experiment that we have done with a relatively small neural data set that we collected a while ago. And I have a subset of that consists of front camera images from highways in Sweden. And for this data set of around 10,000 images, we have solved the task of road classification, which means that for each pixel in the image, the task of the neural network is to classify this image as either belonging to the road or as not belonging to the road. This can be, I mean, there are a lot of subtleties here about how you define exactly what belongs to a road and not, but let's assume that someone has thought about all these subtleties, as indeed someone has to make annotation guidelines to get the annotations that we do have. So someone has thought about all the possible edge cases and made annotation guidelines, and we have annotated these 10,000 images. We split them by date into a training and validation set. But now, in this case, we do have annotations for all these 10,000 images, but let's pretend that we only have annotations for 2,000 out of the 8,000 training images. Let's ignore the validation set for the moment. So assume that we have labels for 2,000 images, and we have trained the network, and now we want to improve our performance. How should we select the next 2,000 images that we want to annotate? Now, in this case, we select 2,000 images at once because for this more realistic problem, we cannot instantaneously retrain the neural network. You have to. It takes a few hours even with this small data set, and of course, for a real data set, with a big neural network and a very big data set, it can take days. So it's not realistic to get one data point back at a time and retrain the whole network, and then ask for another image and then retrain, and ask for another image to annotate and retrain. So you have to get annotations many at a time. All right. So in this case, we can select 2,000 more images. So what images should we choose? Well, first step, let's train the neural network on these 2,000 labeled images. So just normal supervised learning again, using 2,000 images, and to solve this semantic segmentation task, as it's called, to classify each image into each pixel into either the road category or the non-road category. And now we have selected 2,000. We have labels for 2,000 images already, and we want to select 2,000 more. So to be able to try to get a feeling for what would be an informative image to get labeled for, let's now visualize our performance on these 6,000 so-called unlabeled images. Of course, we have the labels, but we pretend that we do not have them at this time, that we need to query for them. So what's shown here in this web page is a random sample of these 10,000 images. Let's see if I can get my mouse to show. Yes, here it is. So what you see in these images, and to explain what you're seeing here, is that we have the input image, and I have put an overlay on top. So the more blue the stronger the blue overlay, the more confident we are in that this class belongs to the road. And of course, and the white lane markings, they look completely white, but they're also part of the road. Anyway, so if you look at these images, what you see that for a large fraction of them, the neural network does a really good job already. So even after being trained on only 2,000 images, this image handles basically perfectly, except for the far end here. Similarly for many images, other images. This one, it looks like it does a really good job already. This one also is basically perfect. And this one. So basically, if you were to send this image for annotation, let's take this one as an example, you wouldn't learn anything at all because the neural network can already handle this situation perfectly after being trained on only 2,000 images. So why is it that the neural network does this so well? Well, it's a very simple problem most of the time because this is a very simple environment. Highways are designed to look the same most of the time. So for a lot of the time, highways look exactly the same, and a very small data set is enough to do well on it. But of course, it's not enough it's not enough to train a neural network that we want to use in the real world, because every once in a while something different happens, and you have to be able to handle that also. So let's see if I can find an example. Yeah, for example, in this case, the neural network is a little bit uncertain about how to handle this situation. So in this data set that mostly contains of highway images, it's not so used to this situation where you're leaving the highway, so it doesn't handle that perfectly. Tunnels are also a case that is often handled very poorly. So this is an example where it handles a tunnel really poorly. Because tunnels, they do not happen very often. So if you just randomly sample in highways in Sweden, then you will have a quite small fraction of tunnel events. And the lighting conditions in a tunnel are, of course, completely different compared to if you're out in the open. So therefore, tunnels are usually often a problem case. So in this case, the neural network doesn't do so well. So if we were to select this kind of point for annotation, then we might learn a lot. So is there any way to find these images? Well, let's try to extend this toy model we had. So in the toy model, we could compute the expected information gain according to the neural network's estimate of the probability distribution. But in this case, what we have is a classification task for each pixel. So basically, for each pixel, we can define an expected information gain or an entropy. And if we average that over all the pixels, then we'll get some kind of measure of the uncertainty or how much the network might learn from this image. So let's take that as a measure and select the 2,000 highest scoring images according to this measure and label them and see how that works. So just to get an understanding for whether this could work well or not, what I show here is again a random sample of 1,000 images from the so-called unlabeled set, the ones that where we can choose more images to pretend that we label. And I have measured this average entropy of all the pixels and sorted all these 1,000 images according to this score. So if you're in the far right here, like in this image here, this is the part of the unlabeled data where you have a very low entropy. So these are the images that would not be selected for annotation. And if you look at these images, what you see is that most of the time out here you really have these kinds of images where the neural network already makes a very good guess. So for many of these images, you would learn very little by sending them for annotation. So it makes sense that you should not annotate these images preferentially. Whereas if you go to the opposite end of the spectrum, the images with a very high entropy, you see these weird cases where the network doesn't know what to do. Here it have very strange lighting conditions. Now, you might not learn so much from this because it's very hard to know even for a human annotator where to draw the road classification line. But if we take the next example, it's also a difficult one. The windshield wiper goes over the screen, so you don't see anything. Let's go to the next one. Here we have a very interesting example. The exit of a tunnel, the lighting conditions are really difficult. You have a high dynamic range, and probably in this 2,000 images that have been before, you haven't seen a single such example, or very few at least. So the neural network really doesn't know what to do with this part. Whereas this can definitely occur in the real world, so you need to handle the situation. Traffic jam. Apparently, the neural network probably hasn't seen so many traffic jams in this random sample of 2,000 images, so it doesn't know what to do with it too well. So probably you would learn a lot from annotating this image. Let's have one more. Here we have some really strange lighting conditions again. Again, a sort of semi-traffic jam where it doesn't really handle the barrier very well. So here you could also learn something probably. Let's do a few more. Some kind of traffic jam, windshield wiper, strange lighting, a tunnel that it doesn't know what to do with. So what you can see from this is that it seems like the images here in the left end of the distribution are often these kind of cases where the neural network cannot handle them very well. So that indicates that this selection criterion might work pretty well. Sorry, so let's go to the results and see how it works. So what I have to show here is on the y-axis is a measure of the error that this neural network does on this task. It's IOU, it says it should be 1 minus IOU actually, because it's an error metric instead of a accuracy metric. What you see here are these diffuse crosses are 20 different runs that I did to get statistics, and the heavy cross is the best estimate of the mean, and a 95% confidence interval of where we think the mean error is. If you do this procedure many times, you select samples randomly, 2,000, and then you train in your network on it, and then you measure the accuracy on the validation set. Now this was for training on 2,000 images. If you instead train on 4,000 randomly acquired images, then the error rate drops as expected. So it drops here from maybe 4.9 to 4.3 or something on average. But if you instead use this active learning criterion of selecting the images with the highest average entropy, then the performance, the error drops a lot more. The performance increases a lot more. So the error drops roughly twice as fast to maybe 3.8 instead. So for this problem, it seems like this idea of actively selecting points, it works really well. And qualitatively, we can see how it works in a tunnel. So as we saw, there were a number of tunnel examples that were actively chosen. So you would think that this neural network will do, that has been trained on the actively selected images, will do better in a tunnel. That's indeed what we see here. So both these networks, they don't do a very good job, but at least the one on the right is more consistent and does a slightly better job. And in fact, it's not strange that it does such a poor job, because this network was trained on only 4,000 images, and that's a ridiculously small number of images to train a neural network on. So it's not surprising that it does badly, but it's encouraging that it does, or interesting that it does a lot better at least than the one that has been trained on only random images. Now to wrap up, there are of course many more things you can do. So, for example, so I'm going to want to mention a few of them about the next steps you could try here. So one of them is the selection criterion we used was to average the pixel entropy over all the pixels. Now that doesn't really make sense. This is like assuming that all these million or so classification tasks, one for each pixel, that they're all independent of each other. That if you learn that the given pixel belongs to the road, that doesn't tell you anything about its neighboring pixel, which is not true. So there are a lot of correlations between the pixels, and so the information content that you get is not really well approximated by this assuming that all the pixels are independent classification tasks. Another thing is that we have used this output of the neural network as a probability metric. But in fact, if you just train a neural network like this, it often gives you a very poorly calibrated probability estimate. It's often overconfident. So if you were instead to use an ensemble of neural networks, you could expect to get a better calibrated probability distribution. Or if you used something called Bayesian neural networks, this is a method or a family of methods for getting neural networks that are supposed to be better calibrated, to have an output distribution you can trust. And this is something you can try. Another thing is this: if you select 2,000 images at the same time and you select all of them by the same criterion, there's a risk that you select many very similar images, which isn't beneficial. So in this case, it worked out all right anyway, because we only had 6,000 images to choose from, so there weren't so many tunnel images that you could pick. But in the real case, you would probably have a million images or millions of images to pick from. And then if you use the same criterion to just pick all the images, it's possible to select 2,000 extremely similar images, which wouldn't help you improve your network very much. Further, this metric that we use, the IOU, it's not obvious that this is a relevant metric. If you improve on the IOU, does this automatically mean that you can trust your network more to make driving decisions? And not necessarily. It can be strongly biased to things that happen close to the car. But so if you have something, if you make a false detection far away from the car, this can be still quite bad for your planning, but it doesn't influence this IOU metric very much because there are so few pixels as you go far into the future, into the forward direction. Yeah. Further, we had this very small data set, and of course in the real world you have larger data set, which brings all kinds of problems. Another interesting thing to think about is that if you select images actively, you want to select the most informative images, but often this means that you select difficult images and they might take longer to annotate. So say that you get, by this active criterion, maybe you can get as good performance as for the random sample in just half as many images. But if each image takes twice as long to annotate, then you haven't really gained anything. One more thing I want to mention just at the end is that in this case we send all whole images for annotation, but often if you have a well-trained network, it will handle most of the image perfectly, and there will be some part where you can learn something. So ideally, we would like to only annotate that part where you can learn something. Anyway, I'll end my talk here. So if you think this sounds interesting, please have a look at our career website, because we actually do have open positions at the moment for the deep learning and other computer vision teams. Also, you're most welcome to send an email to me if you're interested, or if you have any questions about the talk or anything. My email is down here, erik.werner@zenuity.com. And now I'm open for questions.
Thank you so much, Erik. So we got a couple of questions here. I'm going to start with the first one, and namely, which hardware has to be used to classify the road in this current example? Is this software embedded already?
Yeah, so to be able to train in your network in a reasonable time, I mean, in this case, we had a very small data set, so you don't need a monster to train this new network, but still, you probably want some kind of GPU to do this. And of course, for the real production networks, you want multiple GPUs, and it has to run for a long time. Let's see, what was the other part of the question?
Is this software embedded already?
Right. No, so this particular network that we used here was just a small, relatively small network that was used just for this experiment. So this is not a network that we have embedded, but of course we do have networks in production. So networks, yeah, Adam will come a little bit more closely on to this, but yeah, this particular network was just for a small experiment, but we do have networks deployed to cars that are out and running. Yes.
Okay, so the next question was, how big of a data set do you need in number of images for a robust classification flashed on a vehicle system?
Yeah, that's a very good question.
Okay.
Okay, I continue with the next one. What would you do with these high entropy images when you discover, for example, edge cases with a lens flare? Do you skip them? Would you then have to design a new network to figure out when this happens to set guards in check so that data will not be used?
Mm-hmm. Yeah, that's right. I mean, this kind of thing like a lens flare, it will happen in the real world, so we have to handle it. And there are different ways to do that, but basically you need to be able to tell that in this situation we do not have a good view of the road. So this uncertainty has to be communicated to the planning systems so that they know that at this point in time we cannot see further than say 30 meters or whatever it might be. So that's a very important question, and you need to think about how to handle it.
Okay, we have actually a lot of questions, so that's very nice. I'm happy that people are engaging in discussion. Since this meetup was supposed to be face-to-face, but it's online instead, I'm very happy. So keep going, guys. So the next question is, what if we simply choose images that are visually dissimilar to the annotated set?
Yeah, that's also a good one. This is also a part of the active learning literature, which is about algorithms to do that in different ways. And then you have the problem of how to define in an automatic way what's a similar and dissimilar image. But there are active learning algorithms that try to solve this task. So there's something called the core set algorithm if you want to read more about it. So, but basically that's another approach you can take, is to try to find as many dissimilar images as possible.
Okay, nice. Next one. Was the actively chosen images selected using the same training of the first training iteration, or was the 2K images chosen on a newly trained network?
I'm not sure I understand the question. So the procedure is that you select 2,000 images randomly, then you train a neural network on those 2,000 images, and run the neural network on the 6,000 images that we pretend that we don't have labels for, and score them according to this average entropy criterion, and use that to select 2,000 more images to annotate. And you get the labels, and now you have 4,000 images, and you train a new neural network on that. And each such procedure gives you one of these green points here. And each of these gray crosses you get by doing the same, but just adding random images. And then I've repeated this procedure 10 times for the active and 10 times for the random one, and gotten this average error. So for each of these dots corresponds to a new random split and a new training of the network and so on.
Okay. Do you retain the network on the actively selected samples, or do you train a new model on the 2K samples plus 2K actively sampled ones?
You can do both. In this case, what we did was, after I had selected 2,000 more cases, I retrained the neural network from scratch.
Okay. Is the network a pure CNN or a recurrent of some type?
This is a pure CNN.
Nice. How does this generalize to regression problems? I guess the entropy has to differ.
Yeah, that's so for regression problems, like finding the location of a 3D object, for example, then you have to think of some other way to do it. You cannot. It's not as easy to define an entropy or an information gain in this way. But what the technique that is usually used is to have, again, you try to get some measure of uncertainty, because that, if you're uncertain, that means that there's something you can learn. So to try to get some measure of how uncertain you are about the positioning, and use that to decide what to select for annotation.
Okay, next one. What is your opinion to use the same approach to schedule already existing labeled data in order to speed up training? Example, tackling to have too few images with pedestrians.
Yeah, this is a very interesting problem that I'm a bit surprised that there's not so much literature about it, because there's one big difference here is that in this case, when we select the label, when you select what image to label, you do not know the label beforehand. But if you have the problem where you have a big data set that takes a long time to train on, and maybe you have class imbalance, and you want to instead shrink that to a smaller data set that you could train on faster, but possibly with the same final performance. In this case, you could make use of the label, which should enable you to do all kinds of clever things. So there's not so much literature on this topic, and this surprises me a little bit. But this is something that is very interesting to pursue also, I think.
It looks like your talk is very interesting, Erik, because questions continue. So are similar algorithms used to prove that your functions are safe, or is it only used for training data?
I'm not sure what's meant by similar. I mean, yeah, I mean this is true. So something you can do is that if you want to find, for example, I can answer a slightly different question. So one thing that we have used similar methods for is to find wrong annotation, because this happens despite the quality review that we do. Of course, every once in a while, faulty annotation slips through. And one thing you can do is to use the neural network's output. If you have if the output of the neural network disagrees strongly with the label, then that can even after training, then that can be a sign of that the annotation is not correct. So this kind of thing you can do. I'm not sure if that answered the question, but I've answered a question at least.
Okay, next one is about quality metrics. So what quality metrics do you use, for example, for road surface detection to be able to tell when your method is good enough for a given use case?
Yeah, that's a very good question. I don't have so much I want to say about that, but basically you need to have some kind of metric about how your road classification task, in this case, how that would influence the planning. So it depends on who consumes your output and what do they care about. That's what has to decide what KPI you use or what metrics that allow you to say if you do better or worse.
Okay, and then the next one is if the camera is changed or repositioned, example, another car brand, is this already trained model still valid?
I mean, the validation, so basically you have to, this is not obvious what will happen for a new camera. So in this case, if you have a neural network that's trained completely on a single camera, and then you deploy it on a second camera, which has different characteristics, then you cannot expect it to work as well. And then there are maybe things you can do to get the network to perform better. And then, of course, you can get more label data with the new camera model also. But this is, if you want to deploy the same network or solve the same task for a new camera, then you have to be careful what you do and probably get more labels for that camera or have some clever way of doing domain adaptation to the new camera.
Okay, so questions continue. So we have to give it a stop soon, unfortunately, but a couple more to go. So have you have you tried to run the algorithm for more than one iteration? Question 1. Question 2, have you analyzed what the informative sample are, specific distribution?
So for question 1, yes, that's, I mean, in these kinds of active learning experiments, I mean, this is an experimental setting where you already have the label. So this is for experimenting with different methods. In this case, it's quite common that this is what you do, that instead of just adding label once, selecting what to label in an active way once, you do it one time after another. So you select actively, and then you retrain your network on that, and you bootstrap and select more labels and train on that. So this is certainly something that is quite commonly done, yes. The second question was again?
The second question is, have you analyzed what the informative sample are, specific distribution?
Yeah, this is this is a bit of a difficult problem because the neural networks are something of a black box, so it can be quite hard to tell if you have improved your performance on a certain metric. It can be hard to know depending on it can be hard to know what new data points cause this change in behavior. There is an interesting paper from a few years ago which is called Inference Functions, which tries to solve this problem. So if you're interested in this, I recommend Googling for inference functions, neural networks or something. But this is a very hard problem.
We like hard problems. Okay.
Okay, so the next question, I think we take 2 more questions and then we move on.
Yes, so we have a lot of questions coming up, and we still have Adam and his amazing talk. So the ones that have been sent now at the end, we're going to save them and ask Erik at the end of the meetup. But before we close this, 2 more questions to go. Yeah.
Okay, so the next question was, if this wasn't a CNN, but for instance, LSTM CNN, how would you select images to train on them, since sequences are important?
Yeah, I think it's so. I actually don't think it changes too much because it's still the annotation part is the most. To annotate the image is more expensive than to train for longer. So even if you have a long sequence of images and you just have a label for one of them, you can still train an LSTM on that because you have to propagate from the timestamp where you have the label and propagate it back through time to all the previous timestamps. So this will have very sparse feedback. So this will make your training slower. But on the other hand, the alternative of annotating every timestamp is probably too wasteful. So I think my instinct in this case would be to go with still annotating sparsely and making do with very sparse ground truth.
Okay, so the last one to go, it's a comment on a question before or a question on a question before. So are similar algorithms used to prove that your functions are safe, or is it only used for training? This you already answered, and then the new question is, your approach is highly dependent on annotation quality. How do you measure the quality of the annotations?
Yeah, that's again. This is again a difficult problem because of this fact that it's hard to tell beforehand how a given data point will influence the output of the neural network. But basically, I mean, we have annotation guidelines. And the annotations are supposed to follow those guidelines. And if they do not, then we consider that a faulty annotation. I don't know if I have anything informative to say about this, except what I said in the previous answer, that you can, in fact, use the neural network to make a guess about what could be a faulty annotation, or an outlier in annotations at least. So is it the funny question? Should I try to answer the other ones in the chat, or should I save them to the end?
Yes, we have 8 more questions to go, but let's save them to the end because we want to continue now with Adam.
But an alternative is that I try to answer them in the chat.
Yeah. Yeah, well, yeah, this is something that you can do as well. And then we're going to publish all of them so it's visible for the public. Okay? And then you're answering them in the chat.
I think that's a good solution.
Okay. In the meantime, we continue with Adam. So I'm leaving it over to you.
All right. All right. Hello, everyone. This is Adam. So I want to talk a little bit today about 3D object detection, which is another one of these perception tasks that Erik mentioned in the beginning. So his example was about road classification, and this will be about 3D object detection. And this is a nice example to talk about for autonomous driving because it's very intuitive that if you want to have a self-driving car that's out on the roads, it needs to be able to detect all the pedestrians around it, vehicles, signs. Yeah, simply it has to detect all the objects that are around the vehicle and has to be able to position them in the world to then properly make this plan and then act on it. So I've been working here at Zenuity since the autumn, basically, with object detection. And before that, I was doing my thesis on multi-sensor object detection in Munich. So let's get to it. So before we dive into the 3D part, let's just do a quick recap on 2D object detection. So here in this image, you can see an example of just that. We take an image, and the task is simply to find all the objects we are interested in this image, draw a simple rectangle around them or a bounding box, and then assign a class to every object. So in this image right here, you can see that the blue class corresponds to small vehicles or cars, basically, and the orange class corresponds to these larger vehicles, such as, for example, trucks or buses. So this is 2D object detection, and this is a very sort of a traditional deep learning problem that's very well studied. And it's basically, this is maybe a little bit making things too simple, but it's an easy peasy problem to solve if you have these good data and you have written sort of good guidelines for your annotation, and you have, if you have solved the data problem well, the actual designing of the network and training the network is not so complicated. So this is what we show here, this pipeline basically that Erik was talking about also. the path from unlabeled data to sending it off for annotation, getting some labels. You plug it into your CNN training pipeline, and then you have this active learning feedback to continuously improve the network. But so what about going to 3D? What are we interested in here? So for 3D object detection, we basically want to extend this concept from the 2D object detection, where we draw a simple rectangle in the image, to the real world, and this then could correspond to a 3-dimensional box. And for every such box, we basically need to predict the class, or car, pedestrian, etc. And then also for the box, we want to predict the real world coordinates, then not image space pixels, but rather like how many meters away is this bounding box? How is it oriented? What are the sizes of the bounding box? Again, then in meters. And you could represent such a bounding box in many ways. You could represent it by sort of defining every single corner, or you could represent it by defining the center point and the dimensions, and there are basically limitless possibilities. But in the end, you want to contain every object in such a box. And so here's an example of how this would look. We have exactly the same image as before, but now if you look closely, instead of having just a 2-dimensional rectangle, you have a projection of exactly such a 3D box. So you get this more, you can sort of get a little sense of the depth. And to the right of the image, we have a top-down projection, a bird's eye view of the scene, where the black lines correspond to the field of view of the image. You can see as we go further away, we of course see a wider field. And then all these rectangles are the various detections. So this is basically the goal. This is what we want to achieve. We want to take a single image and get this sort of view of the world around us. So now the question is this reasonable to do? Is it really reasonable to take an image and then recover all the 3D information from it? And it can seem obvious that it's easy to do because, I mean, we do it all the time. We walk around with our eyes and we sort of understand exactly what's around us. But there are two things here. First of all, we have two eyes, which help us a little bit because you get you get a stereo perspective. And then the most important part is that we have a lot of understanding of the world. We have lots of experience. And here are some cases that for us humans, I mean, these are some of the funny optical illusions you can find on the internet. But if you think about it, this would be really difficult for a neural network to understand. Like you take the top right picture with the leaf. For us, it's, I mean, if you look at it, it looks like the girl is holding an amazingly huge leaf, but we can immediately understand that it's unreasonable for a leaf to be that large. Therefore, it has to be much closer, held right in front of the camera. And all the other images here are the same kinds of problems. Like we can discard our initial intuitive reaction and understand that that's not actually what's going on. But this is examples of this ill-posed problem. There are many, many possible 3D configurations that would result in the same image. But fear not, this is possible, and we have some human inspiration. This is the Polish handball player Karol Bielecki, who was a really amazing player in the Polish national team. And during one of the matches, I don't remember if it was even in the World Cup, he had an injury where another player accidentally hit him in the eye. I think it was with the elbow, and he lost that eye, or he lost the sight on that eye. And he, of course, was injured for many months, and then he had some rehab. But the amazing thing is that he was able to go back to playing professionally with only one eye. So he completely lost this sort of stereo depth perception and everything, but just from the experience and from the years of playing that he had, he was able to keep playing. And basically, maybe he was slightly worse, but he was still good enough to play in the national team. So here we have an inspiration for this mono camera 3D perception. And so how can we do this? Like, well, what kinds of things could we look for to go from 2D to 3D? So here we have some of these potential cues. So one thing that's pretty obvious, of course, it's occlusion. If one thing is blocking is blocking the view of another object in the scene, then this other object has to be behind it. So this is quite obvious. That in this sense, we can't get an absolute estimation of the distance. We can get a relative estimation of the different objects in the scene. And then another thing that we can use is this relative size. So if we know how large something is, just because out of experience we know that a car has a typical size, maybe it's 1.6, 1.7 meters tall. And then we can know by just sort of looking at the image and seeing how much space this object takes up in the image, and relating that to how big we know the object actually is, we can get a sense for how far away this object is. And then to sort of get the vertical positioning of the object, we can look at the shadow, as we see with these bouncing balls here. So if the object is touching its own shadow, then we know that, okay, it's probably pretty close to the ground or even on the ground. Whereas if we have this sort of gap, as we do right here, then we know that, okay, the object has to be hovering above the ground. And then there are these other examples. You can look at the shading, you can look at the texture gradient in the scene, distance to the horizon line. And then this linear perspective is probably really important, actually. That parallel lines, as we move deeper into the image, they're like parallel lines in the real world are not parallel in the image. This we can also use to sort of extrapolate the depth. So there are ways to get around this limitation. And to just get a little feeling for this, I have prepared a challenge for you all. So if you could just go to this link that I have here on the top. Let's see if I can even highlight it. So if you can go to this URL, www.menti.com, and enter this code right here, we can perform this little challenge. And because of this time delay, I will wait a little bit before I explain everything. I think hopefully maybe some of you have started to pop in now. So the challenge is very, very simple. You have an image right here, and I just want you to guess roughly with these sliders that you will see here in Menti. Just roughly guess how far away are these three objects. And to give you more of a fair chance, I'll tell you also that the camera that's used here is a 30-degree field of view camera. And this means that objects probably appear to be closer than they actually are, just to give you hints. And let's see here.
We're gonna give you a couple of minutes so that everybody can log in and start answering, but this is gonna be very interesting to see if people are going to guess correctly or not.
Yeah.
We tried this, me and Amanda, before the meetup, and we were quite wrong, or?
Yeah.
It's harder than it looks.
Yeah.
I mean, we do this all the time when we're driving and we're estimating the distance to everything, but we usually don't really do it in these absolute terms.
No. So it's going to be very interesting to see now what people are going to answer.
Oh, wow.
We can even see how many attendees are there in menti.com. So we can wait a bit.
Yeah.
I can see that people are dropping in all the time.
We can see it's very interesting, especially for this truck. The range of guesses is really large.
Yeah, that's true. So what was the minimum and the maximum for a truck?
I don't know if we can see the exact numbers, but it seems to be somewhere between like 15 to 200 meters away.
People can see this on the screen, right?
Yes.
Mm.
So I guess this is a little bit of I'm biasing the results by showing you this live. But I think it's fine.
That's actually a biasing of it.
Yeah. Okay, maybe we can continue now. We've gotten a lot of votes. I guess the only point I want to illustrate here that it's really difficult. It's not at all trivial to make this guess. And I can show you the correct answer. Yeah, so you see the most nearby vehicle is 24 meters away. So here actually the averaging of the crowd, or what do you call it, the wisdom of the crowd worked pretty well. If we average all the guesses, we get really close to the actual distance. For the other car, it's a little bit worse, and for the truck, we're off by 40-something meters. So you can see this is a really difficult problem, and I mean, even if we design our neural network perfectly and we have like an amazing algorithm that can learn anything we throw at it, we still have to somehow figure out the truth for this. We have to get the ground truth. And we obviously can't just use an image and give it to an annotator and say, hey, tell us how far away everything is, because it's just too difficult.
Maybe for people that are not that into the topic, can you explain what's ground truth?
Oh yeah, sorry, ground truth. This is basically what Erik was discussing in his talk, the labels, the sort of the signal we give for the neural network to train the correct answer, basically. So here the ground truth would be 24 meters, 36 meters, and 155 meters. So to solve this ground truth issue, we have the LiDAR here to the rescue. So what is a LiDAR? So as you hear, it sounds a little bit similar to radar. This is not by accident. The little illustration here to the right tries to show how this works. So basically, you have a laser beam that sort of sweeps around the scene, and it sends out these pulses or some modulated frequencies or something. Basically, what you can do is by sending out this beam and then listening for the echo, you can figure out how far away sort of the object that caused the collision or the bounce back of this beam is. So just measure the time, you know how fast light travels, and then you know how far away it is with pinpoint accuracy. And then we can also measure sort of the intensity of this echo that comes back. And this gives you additional information in the form of reflectance. So you can sort of, like a traffic sign will be much more shiny than the regular asphalt road, for example. So this is the LiDAR sensor. And typically here you have one beam sweeping around. Typically you would have many more arranged vertically and then sweeping around the scene. And this would give you a point cloud that looks something like this thing I'm showing you here. So if you've never seen a point cloud before, it's maybe not super easy to understand what's going on. But if you look sort of to the right, you see there's a row of arranged parked vehicles. And then to the left, you can see a bicyclist and I guess some trees or something there. But the really amazing thing with this point cloud is that this gives you a more native representation. Here you have actual 3D measurements. You have the distance. You have the sort of, by looking at multiple points, you get a feeling of the aggregate size of objects and everything. So this we can use to get accurate 3D object detection. And how can we do this in a neural network? So since the point cloud is just a list of points, basically, you saw like a large collection of points, it's not very trivial how to apply our typical convolutional neural networks, for example, that we use in an image. Because in an image, you have a structure, you have rows, you have columns, it's very clear where every pixel belongs. Whereas for a point cloud, it's more like a huge unordered bunch. So to make it more like an image, we can use this voxelization approach where we convert the world to a grid. Sort of like Minecraft, where there's like the world consists of small cubes. And then for every cube, we encode information about what points ended up in that cube. And in the simplest possible way that actually works really well, you would just say a value of 1 if the cube contained any points at all, and a value of 0 if the cube didn't contain any points. This is one approach to this. And once you've done this voxelization, you now have a sort of grid-like structure, either 2-dimensional or 3-dimensional, and then you can just plug this into a convolutional neural network and train it as usual. So this is sort of a trick to work directly on these point clouds. And here I have a neural network that does exactly this. This is Voxel FPN, is basically the top-ranked network on a public benchmark that uses this voxelization approach. And I'm not going to go into too many details because that's not the point. I just want to show you really quickly how such a network could look. But this network basically does many such voxelizations with different resolutions. So basically, the size of these cubes, how big are they? You do this with a couple of different resolutions, and then you process that with some convolutions, and then you combine them in different ways to aggregate sort of large features with fine details. And then at the end, we just apply some convolutional head to output the bounding box detections. But so this problem, this is not really a sort of, it's more of a hack to work with the point clouds with our known convolutions. It's not really, you lose some information by doing this discretization into grids. So another approach to work with point clouds is this PointNet approach that popped up a couple of years ago. And the idea here is that we actually work directly on this unordered chaotic list of points. And it's a very simple approach that works surprisingly well. You just take every point, you run it through a very simple multi-layer perceptron, which is just like a couple of neurons and a fully connected neural network. And you do that separately for every single point. And then you need to combine that. And to combine it, you need an operation that doesn't care about the order of the points. So for example, just taking the average, that would work because no matter how you order it, the average always gives you the same answer. Or in this case, they use the max pooling. So for every sort of feature in this neural network, you just take the point that had the highest value and then you take that value. And once you've done this combination, you run it through another small such multi-layer perceptron, and then you have your final classification score. And this trick then lets you work directly in the point clouds without doing any sort of discretization or losing any information. So it's very powerful. And here's a network that's even more complicated that works in such a way. And again, don't worry too much about the details because you could probably talk about this network for at least half an hour. But the idea is that you take your point cloud, you run it through a sort of more fancy version of the point net. There have been some iterative updates to it. But you run it through such a point-wise neural network that then gives you, for every point in the scene, you get some abstract features. And then based on these features, you can classify whether they belong to an object or whether they belong to the background. And then you get sort of a rough estimate of the bounding box for every such point. And then you take all the foreground points, you take the rough bounding box estimations, you crop out that part of the point cloud around the sort of estimated bounding box, and then you run another point net on top of that. And with this sort of the second point net can then work in more high detail and make a really accurate final prediction and say whether this proposal was actually a detection or not. So it's a two-stage approach. First you make some guesses and then you refine those guesses. But in all stages we work directly on the point cloud. We never do any discretization, so it's pretty cool. And in action, this network looks kind of like this. So you can see that both in the image and in the point cloud, it seems to work amazingly well, actually. It detects basically every object and it detects it very precisely. The downside with this point arsenal approach compared to the previous voxelization approach is typically the runtime, because I mean, you saw it, it does a lot of processing, and the convolutions are usually more optimized in these point net approaches. So there's some trade-off here between runtime and final accuracy. Okay, so this was a long detour talking about LiDARs and LiDAR neural networks and stuff like that. But what we're actually interested in here is how can we train a network to work only on a single image and then output 3D. And they might ask yourself, why is that what we're interested in? Why not just use the LiDAR since it's so amazing? And then one problem with LiDAR is that it's pretty expensive. Another problem with the LiDAR is that it also doesn't always work. For example, in rain, it has huge problems because the raindrops interfere with these laser beams. And finally, even given all of this, and even given that you have a LiDAR on your vehicle, you just really need redundancy in the system in the autonomous car. Because you can't just rely on a single point of failure, and then if that doesn't work, your whole system sort of comes crumbling down and breaks. So you need multiple ways to interact with the scene and to perceive the scene, and then you have to combine those ways to your final sort of model. So, in short, we want to use the LiDAR to train the camera. So we have an updated version of this 2D pipeline here, where you have the same unlabeled images, but also attached to it you have a LiDAR point cloud. So this means, of course, that you would have to have a LiDAR mounted on your data collection vehicles to drive around. Otherwise, you can't generate this 3D ground truth, at least not in this way. But then you send these pairs, you send often for annotation. It can be human annotation. You could even do some automatic annotation with such a LiDAR neural network that I just showed. And then you get back images with 2D and 3D labels, and you plug them into your training. And here's sort of a more in-detail approach for how a neural network can actually learn this step. I mean, I showed you this slide before with occlusion and relative size and stuff like that. And this is exactly this, but in action. So if you have a neural network that has an image with a vehicle in it, it can, first of all, it can estimate the size of the vehicle just sort of by making a semantic prediction. It has seen many vehicles before, and it knows that a Volvo car is typically blah, blah, blah meters high. And this is sort of a prediction that the neural network just makes straight out, so it doesn't have to. It's like an image classification basically. And then by counting the apparent, like you can just count the number of pixels in the image that this car takes up, sort of vertically, And you can compare that with your guess for how high the car actually is. And then using the focal length, which is something that you know the focal length of the camera in your vehicle. And if you have a neural network that trains on many different cameras, maybe you can input the focal length, or you can learn to normalize for it. So all these things are known. And then you can estimate the depth by just taking the simple ratio that is shown here in the top right corner. So this is like a very simple example showing you how you can infer depth from an image. But then it's not quite as simple as that, because if it was that simple, we wouldn't need to build this complicated neural networks, or we can make a network that only guesses the 3D height and then compute the rest ourselves. And here's an example that shows that this is a very nice paper that tries to study how neural networks actually do depth estimation in a single image. So here you can see a scene where this white car is sort of just pasted in. It's a fake car, doesn't exist in the original image, just added there to see how the network responds to it. And then you can see that even though we've shrunk the image, the car significantly in the image, it's still, to us humans, it's obvious that the car isn't like 200 meters away. It's really close to us, based on sort of the shadows and the position relative to the road and how high up it is in the image. And if you look at the depth map here, which is the bottom row, where brighter values mean more nearby depth, you can see that the network also sort of doesn't predict the vehicle to be much further away when we shrink it. So it sort of learned, it of course also learns this relative size, and it learns some other cues, and it combines all of this to make the final 3D estimation. And now finally, let's dive into some networks, how they actually can look, these networks that perform 3D object detection from a single image. Water. Okay, so the first approach I want to show you is when you just take a regular 2D object detection network and you adapt it to perform 3D object detection. So what I show you here is EfficientDet, which is sort of one of the most recent state-of-the-art architectures. Was published by Google sometime early this year, I believe. And it uses basically an image classification backbone, which is this thing you can see here to the left. And then on top of that, you add a feature pyramid network, which basically takes sort of these intermediate feature maps from different resolutions in the sort of backbone network, and then combines them over and over and over. You can see this complicated graph here, but it's basically, you just want to sort of make use of the most downsampled layers in the network, contain very many features with sort of lots of semantic information, whereas the less downsampled part of the network, of course, have a better resolution and therefore can resolve all the fine detail in the image. And by combining these over and over and over, in the end, you end up with sort of the best of both worlds. And that's what this complicated graph here in the middle does. And then at the end, you just attach a couple of convolutional layers as this head that then predicts the actual 2D detection. And to convert this to a 3D object detection network, we can just keep the existing heads. You keep the classification head, you keep the bounding box and regression head, and then just add some additional heads. And in this image here, you can see that an example of these heads, and there are many ways of constructing these heads depending on if you want to detect some key points or some bounding box corners, but this is maybe the simplest way, where just directly you just estimate the depth as a single value and say this is how far away the bounding box is, and then you determine the size, just predicting 3 values, and this is how many meters, like how large it is in meters, and then finally the orientation, which is basically just how this bounding box is turned, either in maybe a ground plane for autonomous driving, because things are usually in a plane, or you can orient it more 3-dimensionally and predict every single rotation, depending on what you need. But this is sort of the naive approach. You just take it to the network and you add additional heads, and it actually works very well, this approach, and many state-of-the-art architectures use this approach.
Very interesting and very bright presentation.
Yeah. I think we have to try to wrap up, but we're almost there.
You don't need to hurry up.
And then we have this other approach, which is a pseudo-LiDAR approach. And this is a more recent, like sort of this previous approach I showed you, people have been trying it out for a while. And then the pseudo-LiDAR popped up 1 or 2 years ago and became very popular because it sort of tries to leverage the great performance we get from the LiDAR object detection networks. And because the LiDAR is working so well, a lot of research goes into LiDAR object detection network, and then the networks work even better. So this is sort of a trick where you take a single image and you try to construct a fake LiDAR point cloud out of it. And you do this by first generating the intermediate representation of a depth map. So you take your image, you convert it to a depth map where every pixel just describes how far away that pixel, the contents of that pixel are. And then you can take that depth map and turn it into a point cloud. So here it just shows basically the same thing, but more spread out. So once again, you take your stereo or mono images, you plug them into your depth estimation network. This network spits out such a depth map. And these networks are sort of also well studied. This is the original pseudo-LiDAR paper. They just picked such a network off the shelf. And then they didn't even retrain it or anything. They just said that here we take a depth network and then we use it to get a depth map. And then once you have such a depth map, you can use, again, these camera intrinsics, such as the focal length we discussed before and some other intrinsics, to figure out where this pixel, sort of you figure out the ray alongside which this pixel goes out into the world. And then you just say that the depth value is how far along this line we go. And then you say that at the end of that line, here is our point, which we will use to construct this pseudo point cloud. I hope that made sense.
Yeah, it made you got a comment. It's a fantastic explanation. So it makes sense, obviously.
Nice. And this point cloud, it doesn't look exactly like a real point cloud. I can actually go back to the slide and show you. You can see that there are sort of some smooth lines, like it's not as sharp and as crisp as a LiDAR point cloud, but it's still, in this example, it's obvious that it's still enough to sort of detect the vehicles. So you have, once you have the pseudo point cloud, you take it and you plug it into one of these LiDAR detection networks that I just showed before, like for example, Point RCN or Voxel FPN or any of the other number of LiDAR networks. And then, of course, you have to retrain it to learn to work with the pseudo-LiDAR, of course. But then you sort of get this 3D predictions. So this is the alternative approach. And then there are, of course, pros and cons to both of these approaches. So the nice thing with the pseudo-LiDAR is that it sort of performs these 3D detections natively. So you don't really have to worry so much about like image invariance depending on where the object is seen in the image and stuff like that. It makes things very simple. You just you're working directly in the 3D world, so then your predictions sort of are in the 3D world. You don't have to do so much post-processing to reconstruct them accurately. And also has pretty high localization precision, especially so most of these research papers that look at these different methods and compare them. They work on Kitty, for example, or yeah, I guess Kitty is one of the most popular data sets, which only has objects up to something like 80 meters away. And in these sort of short-range scenarios, this pseudo-LiDAR approach has a really good precision and better than the more sort of direct image-based networks. And with the stereo depth estimation networks, it's actually starting to approach the LiDAR performance. There's still, it's still not quite there, but the gap is shrinking pretty fast. But there's also some downsides to this LiDAR. Of course, first of all, you need to have a separate monodepth network, which is extremely crucial for the quality of the actual object detection at the end. Because you can imagine if the depth estimation is poor, then like the object detection will be really off. Yeah, it lives and dies by this monodepth network. Another con is, at least in this sort of initial approach I showed you here, you lose a lot of information from the image. You lose sort of the color, the texture, reflections, all of this that can actually be important to make the correct classification. Another downside is you don't get these 2D detections natively. Like you can take a 3D bounding box and project it into the image, like I showed you before. But it doesn't really, if you just do that and you try to, from that, create a 2D bounding box, that 2D bounding box will not really fit tightly and it will be quite low quality, basically. And the final downside of the pseudo-LiDAR approach is that, and this is like it's hard to say this absolutely, because it's not a fundamental limitation of the approach, but typically it seems to have a lower sort of, at least 2D recall for objects that are very far away, because those objects are much easier to detect in the image place where the pixels are close to each other, and simply, even if an object is only like 5 by 5 pixels, you can detect it in the image. Whereas in the point cloud, those will only be 5 by 5 points that can also be far apart from each other. So basically, the direct image space regression would have better recall.
Lots of talking.
Yeah, no, I'm not used to so much talking so fast. Okay, so I have a final challenge for everyone to wrap this up. So if you again just jump into Menti with the same code as we had before.
Now maybe we can give some more time to the attendees to log in and answer their questions.
Yeah, that sounds good.
Because
I don't think from my voice.
Yeah, exactly. So 2 good things in the same time. Because I think yeah, not every person has maybe used Menti, so it takes some time to go in and log in. And it's, I think, very interesting for our attendees today to do such challenges, since this is real time.
Yeah, yeah, this is as interactive as it gets, I guess.
And we've been having also some new questions published in the meantime, so we've noted them down, and we're gonna ask you after you're done with your presentation, Adam.
Okay, nice. So just to, while people are voting, just to give some background here, what this images means, if it's not super clear. These are 3 sets of these bird's eye view plots that I showed you before, where on the left-hand side, we have a network that perfectly predicts all the bounding boxes for all the objects except for one. But this one could be very important because it's a pedestrian close to our vehicle. And then we have another network that perfectly predicts all objects that are close to us, but entirely misses everything that's far away. And then finally, we have a network that sort of, it seems to catch everything a little bit, but the detections are terrible. It's like, if you were to use a 3D average precision, you would probably get 0% score on this one. And it's not at all obvious to me also, and hopefully to most of you, which one of these I would choose for an autonomous driving car. I mean, ideally, of course, we would catch everything perfectly, but when we're designing our metrics, we sort of have to think about these trade-offs and try to come up with what should we optimize for, what's the best thing for self-driving.
So let's see, we have some people in, but still lots of people are dropping in, so let's give it a couple of more seconds maybe.
Yeah.
So people can think about it and vote. Did you vote, Amanda?
Yes, I voted.
I'm very curious to see how close you are to them.
Yeah, we seem to have a strong favorite, at least, with alternative B.
And Amanda is also part of our deep learning teams, so extra pressure.
Yeah, did you vote B, Amanda?
Okay, you see some more people are coming in, so.
It's interesting. Yeah, I guess the reason probably why B is so popular is because we catch everything close to us really well.
But now you're giving me some.
Oh no, I'm not saying I would vote B. I probably wouldn't vote B. Can I say that?
You must not.
There is no correct answer here. That's why it's not like the previous challenge where we can answer it.
Okay.
Because we don't know. No one knows. No one knows what is the correct answer here.
Okay.
I think maybe we can probably continue. Maybe we can have some questions on this
we
later.
Can do that.
But thank you all for participating in these Menti challenges.
So there was no correct answer?
Of course there is no correct answer. No.
Yeah,
That would
there's
be.
a question in the chat. Is that on purpose?
Yeah, maybe not. Maybe someone can come up with the correct answer and tell us. I would like to know.
Yeah, I think you owe us an explanation now, Adam.
Yeah. But to summarize here, the main takeaways, I guess, is that one, we can use a LiDAR to teach a camera to then work standalone pretty well. And it is possible to approximately, at least, recover 3D information from just a single image. And of course, I didn't say this in my talk, but we're talking about single image, single frame, so there's no sort of time sequence tricks allowed here. And there are two main approaches in the literature. One is to just directly do these regressions in the image space with a regular convolutional neural network working on the image. And the other popular approach is this sort of pseudo LiDAR, where we have an intermediate step of converting the image to a fake point cloud and then making the detections in that fake point cloud. And the final takeaway, which is maybe the most important also for us that are working with this, is that we need to be very careful when we're designing our metrics to sort of decide what we optimize for, because it's not at all apparent with these methods what is better. It very much depends on sort of the later stages that will consume the perception outputs to try to then make this plan, sort of what they're sensitive to and what's more important. So this is a big challenge. It's, I guess, actually an advantage at Zenuity, because we can sort of work with the whole pipeline, so we can have these feedback loops. Yeah, that was it for my talk. I hope you enjoyed it. And if you have any questions, please ask them now, or also you can just email me anytime at the email down there in the bottom.
Very, very nice. Thank you so much, Adam. Great presentation.
Thank you.
So now we start with the questions. We are a bit over time. We were supposed to finish now at 6:30, but we have a lot of questions coming up, and I still see a lot of attendees. I still see a lot of attendees. So if you guys have some more time, a couple of minutes to hang out with us, we would be happy. So I'll start now with the questions. Let's see. First one. Even when you can see other cars, if they're on the other side of the road, it might not be helpful for a car. How do you differentiate between the car on the same road versus the one on the other side?
Yeah, so this is a good point, and I guess this ties into this final challenge that we had about our metrics and what's important to sort of design for. So the network. Like there are a couple of ways to tackle this problem. Ideally, of course, we detect everything perfectly and then we're fine. But to sort of, in the later stages, in the planning stages, differentiate between these different cars, you could have an additional sort of prediction, which is actually, is this on our side of the road or is it on another side of the road? Or you could just look at, for example, the orientation prediction to see that the car is, I mean, you can see that it's a little bit more to the left and it's oncoming, so then it's probably on the other side of the road.
Okay, so next one. Can you use, say, the type of the road and the distance between the lane markers to get an idea of the distance? For example, roads in Sweden with less than 50 kph has a 3-meter gap and 3-meter line with exceptions.
Yes, I think for sure, especially as humans, we can do this because we sort of look at the image in a more holistic way than a neural network. Especially when we're working with these convolutional layers, they typically focus more on sort of the area directly surrounding a vehicle. So counting all of the lane markers up to that vehicle to get a distance for it would probably be very difficult for a neural network. But it's definitely one of the possible cues. And I guess actually, I can jump here really quickly. In this example that we had right here, where the small vehicle wasn't predicted to be far away, it could very well be because the network saw sort of how the size of the vehicle compared to the size of the lane marker, and then figured out that it cannot possibly be 200 meters away.
I think we had another question on this particular picture, actually. So following the example of the fake car with different sizes to determine the depth, what would you expect if you place a huge car around the horizon?
Yeah, so I actually had this image because this paper, they had lots of these different images, but I removed it because I had too many slides. So they do exactly this. They take a huge car and they sort of place it further away to the horizon. And what happened in this case is that the network completely freaked out. It couldn't understand what was going on because it didn't make any sense. So the depth maps got sort of all jumbled up, and they kind of looked like the bad examples that Erik showed in his active learning talk. Like it was clear that the network had never seen this and didn't understand what to do because it didn't look reasonable.
Okay, a lot of questions coming up, Adam. That's great. Thank you, guys. We would have loved to have this meetup face-to-face in order to engage discussions, since all these topics are very advanced and interesting for all of us, but it's functioning with a chat as well. Let's see. The next one is this ongoing research? Are those first experiments, or what do you have, or do you have, how do you pronounce this?
Pseudo-LiDAR.
Pseudo-LiDAR deploying in your data pipeline?
So we have both basically, or like we have different networks for different experiments, and we have both the pseudo-LiDAR approaches and the non-pseudo-LiDAR approaches. But of course, I can't say exactly what we're planning to do in
yeah, that would be good
production.
not to share this information.
Yeah, but I can just say that we have experiments with both of these types of architectures.
If you want to know more of the insights at Zenuity, you're welcome to go to our career website and apply for one of our open positions. Then
exactly.
Adam can guide you from the inside.
Apply and find out.
Okay, next question is, I believe LiDAR is used by police to detect speed. So LiDAR generates live data. Why do you think camera needs training from that data when you can use the live data to do real calculation?
Okay, wait, can I read that again?
Yeah.
LiDAR generates live data. Why do you need training from that? If I understand this question correctly, it is basically why don't you just use a LiDAR in the car, since it can do these 3D detections more accurately? Why do we need to sort of do this middle step of training a camera and then having the camera in the car? Is this correct? Oh, I guess I can't give you. I will answer that question. So I tried to allude to this a little bit earlier, but one reason for not using only LiDAR, I guess, for this is that LiDAR has many fault cases, such as, for example, heavy rain. It just doesn't work at all. And it's also very expensive with LiDARs. So just for sort of economical reasons, I mean, we want to put this in a car and sell it. So sometimes there are trade-offs. And in that trade-off, if we can get close enough to LiDAR performance with a camera is much, much, much cheaper to mount on the car than a LiDAR. And then the final, maybe most important point is that we really need redundancy for the autonomous driving perception systems. So we typically sort of solve the same task in many different ways, and then you can combine these different solutions to hopefully the different solutions can cover up for their respective fault cases. Oh yeah, that's where the camera is.
Yeah, that's why I'm sitting close to you.
I thought you were just getting,
You see, we have lots of fun having a meetup here at Zenuity. So next question is, do you think it's realistic to rely on only camera, no LiDAR, for full autonomous drive in all scenarios? What about in difficult scenarios, for example, detecting pedestrians without reflexes during nighttime? That was an interesting question.
It's a very good question. It's probably not realistic to only rely on camera for everything, but there are, of course, many other sensors also. There's, for example, radars you can use to detect objects, and there are LiDARs. So, and there are different kinds of cameras. It could be night cameras that can sort of solve exactly this example that you're mentioning here. But I think it's a very good point that we need a wide set of sensors that can cover up for their respective weaknesses to solve the problem entirely.
Okay, so going further then, what year are self-driving cars gonna be on the roads again? there definitely should be a correct answer to your last Menti question soon.
Yeah.
Well, there
Hopefully.
was two questions in one.
Yeah. I guess with these what year predictions, it's always really difficult, and I of course don't have an answer for it. I think it's many years until we have self-driving cars that can drive exactly everywhere without any sort of restriction or
You sure
stuff.
about that?
I mean, next month maybe.
Anything about the Mentimeter question?
No, I don't think so. I guess my answer to that is even if we have cars that are proven to be safe enough, even then we maybe don't know the answer to the last Menti question. What is the absolutely optimal metric to optimize against? We can just prove that with whatever optimization we did, we got good enough. But I think it might not actually be the same thing.
Okay, so cool. Even more questions are coming. Very nice. To what extent can synthetic data be used for your approach? 30% synthetic computer rendered and 70% real world data?
So we have done experiments with synthetic data. And I think the main conclusion is that real data is always better, of course. But I don't have a clear number. It turns out that it's really difficult for the synthetic data to really capture all of the sort of the properties of an actual real-world camera, which makes it that if you have very small real data sets, then synthetic data can really help. But if you have large real-world data set, then the sort of benefit of synthetic data decreases slightly.
We have a lot of real-world data, though, correct?
Yeah. But I mean, you can use synthetic data to maybe resolve very difficult edge cases that it's really hard to get real-world data for. So I definitely think that there are benefits in synthetic data.
Okay. Is there a linear increase in accuracy with the number of cameras? For example, is it obvious that stereo cameras are actually doing projection as in the good old days, or is it simply that more cameras on average have less noise?
Oh, interesting question. So I think this depends. For sort of the pseudo-LiDAR approach that we talked about with depth estimation networks, then there is a very clear benefit for stereo cameras, because then you can sort of design also your training to design. You can design your training so that you make predictions on both cameras, and you sort of compare them, and you cross-reference, and you can make lots of tricks when you have two cameras that are viewing basically exactly the same thing. And you can also, of course, use both cameras as input to this depth estimation network to make it better. So in that sense, it is the stereo effect actually helps. And if you have stereo cameras, you can also use traditional computer vision methods for doing depth estimation. But then there's, if you're just talking about the direct in-image object detection network, there's probably also a good point that if you have two sort of non-stereo but cameras, but that they have some overlap, then you can lessen the noise from the respective detections.
Okay, so next question. How do you find out if the LiDAR point cloud ground truth is flawed?
I guess in this case, the question refers to automatically generated LiDAR point cloud. And that is a very difficult question. I mean, I think that's basically the same question as when we talked, when we asked Erik, how do you determine whether your annotation quality is good enough? Because that's basically what it comes down to. And unfortunately, I don't have a good answer to that question. But the same way that, yeah, you have to look at it the same way you would look at your annotations, basically, to find out whether they're good enough.
Mm-hmm. Next one. You said about the problem of the LiDAR during rain. How does camera perform better during different weather conditions, like snow?
Yeah, so there's cameras, of course, are also not perfect in all weather conditions, but there are there's this very nice picture that I said I can't bring up right now, but where you can sort of show the strength of the different sensors, in which conditions they work well and in which cases they work bad. And then you want to basically overlay, you want to use sensors that when you overlay those strengths on top of each other, they sort of perfectly cover up each other. So for example, for rain, of course, a camera works worse during rain than not rain, but it still works decently. Like we can look out through a rainy window and see everything that's going on. And the same with snow, like when it's snowing. If the snow would actually cover the camera, then we're screwed. But if it's just snowing, we can probably treat it similarly to rain, that it's like noise on the image, but it still works. And whereas for the LiDAR, the problem with the LiDAR here is that the rays bounce weirdly and they get bent. For example, by the raindrops, the rays get bent, and then it's very hard to distinguish whether it's a good, if it's a real point or if it's like a bent, distorted point. Whereas in the image, it's quite easy to see that like this pixel was covered by a snowflake, so we can disregard it.
Okay, I see some people are also interested in us sharing this session. So everything has been recorded, and Amanda has also just sent the link to YouTube where you guys can all watch later. Maybe we should also send an email with the link here to make sure that people get this. Okay, next question from Thomas. Basically, I'm wondering if you can do without LiDARs.
I mean, there are definitely companies that are betting on that. Like Tesla, for example, is betting on not using any LiDARs. I think, personal opinion, I think it's doable, but I think it's if you were just to of course, if you were to just in a perfect world put whatever sensor you want, then I would put both a LiDAR and a camera. But I think you can get very far with only cameras.
Interesting. Okay, what data preparation tasks are causing you most trouble? Data cleaning, data selection, data labeling, quality assurance, data augmentation.
This almost sounds like it's a question for Erik. Is it possible, or is it a question for me?
It can be also for Erik. Erik, do you maybe want to join and answer?
I'm happy to join. I don't have a good answer, unfortunately. All of these are tasks that takes that we spend a lot of effort on. It's hard to say that a given one is the one that causes more trouble, and they're all related, of course. Then. So these are all extremely important tasks that we spend a lot of effort on.
Okay. Then we have a comment also from Nima replying to Thomas. It's in public domain that we're doing with LiDAR for production AD cars. Not really sure how to interpret this, but
I guess it means that we're aiming for a solution with LiDARs.
Yeah. So next question, are you using traditional approaches as well for 3D OD in addition to machine learning? I guess that's for Erik, or is it?
I guess it's for any of us. I think this is one of these things that we probably can't discuss too much. I'm not sure. Unfortunately, yeah. I would like to answer everything.
Yeah, sounds good. It's very sensitive, of course, so let's go further. Any work happening with thermal infrared imaging for detecting objects, at least living?
There's definitely literature on this, sort of using infrared cameras or other cameras. Also these event cameras. So there's a lot of work going on with non-traditional cameras.
Mm-hmm. Okay, we have, I think, one, or how many more new ones we have?
Let's see.
Or we don't have any new questions then?
It was a follow-up, I think, but it was posted as a private reply, so I can't publish it. But to the question, is there a linear increase in accuracy with the number of cameras? If you remember that question. There was a follow-up. Actually, I meant for the pseudo LiDAR, and if you have more than 2 cameras, would you have the same linear increase in accuracy if you have 3 cameras?
Ah, I see. Okay. So for the pseudo lidar, okay. So there are, I guess, two again different ways to interpret this. So a real lidar, of course, depending on the lidar, but many at least real lidars, they sort of create a point cloud that's a 360-degree around the vehicle. So in that sense, of course, more cameras help out because you can cover a wider field of view. So if you have like cameras pointing in all the different directions of the car, then you can perform a pseudo lidar detection for vehicles all around the car. Whereas if you only have a camera pointing in the front, you can only perform detections in front. But then if your question is rather sort of if the cameras are pointing in the same direction, if there's a linear increase, I've only actually seen work done on stereo cameras here. I haven't seen sort of triple cameras pointing in the same direction. I would really guess that it's highly diminishing returns after stereo. Because with the stereo, you can introduce this perspective to it. Whereas with 3 cameras, I don't think it helps so much. I would rather have 2 cameras that are further apart so that you get a higher perspective effect, rather than have 3 cameras that are close by.
Okay, so that's an interesting one. What are your main research axes at the moment in terms of object detection? Or is this just sensitive again?
I think this is fine. I think one of the major challenges is sort of covering this, covering the edge cases or covering the cases that are really difficult. And this I guess is not unique to 3D object detection. It's the same for 2D object detection. But this is I would say it's the hardest part, is to not just get good in the sort of average case, because but get good in the difficult scenarios. And this is where I guess also the active learning comes in. That you can use active learning to mine for these difficult scenarios where you're not as good and try to expand that.
Okay, so we have a couple more questions for Adam, and then I was thinking we can go back to Erik, since we had also a lot of questions unanswered from his speech. So Ajay is asking, is all autonomous driving work limited to lidars and camera detection?
So for one, we have also radars, like I mentioned. So that is definitely an additional sensor. And then, of course, me and also Erik, we're working with the vision, like deep learning vision. So we're focusing on cameras. So I guess that's why there's so much talk about cameras today.
And are you a fan of early sensor fusion, late fusion, or no fusion at all?
Personally, I'm probably a fan of middle fusion, where you do sensor fusion sort of within the neural network in the intermediate layers. This is, but I'm also biased. This is what I was doing in my thesis in Munich, like I mentioned.
Okay, cool. Very nice to have such an engaged discussion. So let's go back to the questions that Erik had. He answered some of them in the chat, I saw, but still we can go through some of them. Where to start with?
Maybe Erik, do you have any questions that you want to bring up?
Do you want to answer some of the questions that you wrote, or?
Let's see. I think I understood the question from Michael Sörsäter here. What's about analyzing what are the informative samples? So as I interpreted, it's about, for example, testing how many of these selected samples come from tunnels or from different situations that you can analyze your data by. So the answer is that for this particular experiment, we haven't done any analysis of that kind, but for our real annotations, we keep track of, we slice the data in as many ways as we can think of, according to time of day and location, and if you're in a tunnel or not, or if you're in a city or on a highway. So we try to have very rich metadata we can analyze all our results by. Let's see if there was anything else that I missed. Yeah, so there was a related question from Isaac about do you think it is better active learning, I suppose, is better than manually querying the data based on GPS or IMU data or weather condition? So I think the answer is that I think it's very important to try to make sure that when you sample your data, you have a good variety according to things you can easily measure, like things I mentioned, time of day, and what kind of weather you have, and in what city you are, and or what country, and what kind of road you're at. But still, even if you do that, after a while, it will be very hard. Even if you slice it like that, then you can cover all these different combinations. But after a while, you still need to find these hard examples that you cannot really put your finger on, or you cannot predefine what is it about this image that makes it informative for the image. I think active learning it really complements these manual or handwritten approaches to getting good variety. So trying to find difficult and informative cases that you cannot, for things that you cannot define like that. I think that was the last one. Yeah. The question: what's the best methods to use to avoid or minimize overfitting when training on the training set? This is a big question of how to avoid overfitting through the training set, and there are many regularization techniques, and that are of course important to do. And always the answer is that the best thing to do is to get more data. So that's what I stick with for my answer, if I can answer one thing. Yeah, there was also a question from Jesper about wouldn't you see a selection bias in the active learning for images with fewer road pixel? And not necessarily. So the way this entropy measure, it gives you a very high score if you're close to maximal uncertainty. So a probability estimate of 0.5 for belonging to the road. So you get a high score for images where many pixels are close to 0.5. So if you have a lot of road or a lot of sky, it doesn't really matter. It's more if you need a large boundary or large areas where the network is uncertain. That's what gives you a high score according to this metric. I think that was the last one. Did I miss anything, Anna?
I'm not sure because you answered some of the questions, but yeah,
I think that was everything.
Yeah, if somebody feels like there is another question, they can write again. But in the meantime, a couple of more came, and namely from Niklas, is camera techniques for self-driving cars also applicable for other vehicles as motorbike or cycle or even a boat, which maybe will become self-driving as well? Self-driving boats sounds cool.
Yeah, I mean, I think a self-driving boat sounds very reasonable. A self-driving bike, even a motorbike, but especially a cycle, it sounds very difficult right now, just hardware-wise, because these neural networks, of course, have to run on some hardware, and this hardware consumes a lot of power and stuff like that. So this infrastructure is challenging to squeeze into a car. So I think it will be very, very challenging to get it into a bike. Yeah. But I mean, if we're talking years down the line, then why not?
From a pure detection perspective, it doesn't really matter. You could, for self-driving boats, for example, sure, then neural networks would be the way to go to find other ships, for example, that you don't want to crash into.
Yeah, for sure.
Okay. Given the new photorealistic Unreal version 5 engine, will there be a need for real-world camera data at all?
So from my perspective, I would say that there will always be a need for real-world camera data, just to, if nothing else, to do sort of a final verification, because no matter how much you trust your simulation, you would never trust it enough to sort of say that the car is safe for self-driving, because it's not going to be the final camera, even if you do the best sort of ray tracing, throw everything you can on it. You will always need to have a real camera in the end to do the verification. Now, if you have anything, any thoughts on this, Erik?
Yes, my 2 cents would be that even if it looks extremely realistic for a human, this you can make something look really realistic while still having much less variety than there is in the real world. So I'm sure that the Unreal Engine, you can make things that are indistinguishable from what it looks like in the real world, but I don't think it's at a level where you get the level of variety in textures and stuff that you have in the real world. And we humans, we don't see, I mean, for us it seems to be okay even if it's slightly less variety, but if you the neural networks aren't as, you know, it doesn't help a neural network generalize to a new texture it hasn't seen before. At least not at the moment. That's my feeling for how it is, I think.
Okay, nice. It looks like we are coming to our last question, and namely for validation of sensors, don't you think active learning will introduce biases, and shouldn't, for functional safety reasons, the data selection be random?
Yeah, this is a good question. I think that, as we said, the neural networks, they are basically a black box. So the only way to validate them are by statistical validation. You have to just show them lots of real-world data and check whether it does its job right. So therefore, what you do to train the neural network, it doesn't really have any impact on the validation. No matter how you train it and what tricks you make when you train it, you still have to validate it in the same way. So I think during training you can do basically whatever, as long as you make sure that you don't overfit to the validation in some way. So as long as you're clean about your training and validation set split and you don't cheat in any way, then you can do all kinds of tricks in the training part. And active learning, I think, is certainly one of them.
Okay, perfect. Well, it looks like our meetup comes to an end, half an hour later than planned, but we're happy that we had so many questions and such a good discussion. And we're also planning to have such meetups later on in the future again within Zenuity. We hope that next time we can actually see each other face to face and network and have a live discussion. But if this is not possible, then we would have another online event. But I'm super happy that so many people joined. It was a lot of attendees all the time, even up until now at 7 p.m. So thank you so much for joining and for your time. If you have any questions, feel free to contact any of us. And also feel free to go to our webpage, visit our career website, and take a look at what kind of spots do we have in the teams. Thank you. Have a nice evening and hope to see you soon.